We're now moving on to subtopic 2.2 forces, and some of this I think you'll be very familiar with, having done it previously, but we'll just go through it and make sure that we've all got a good understanding of what forces are about. First of all, let's just define a force. Basically it's a push, pull or a twist is the easiest way to define it, and the other thing to keep in mind here as well is that with a push, pull or a twist, the direction is important. So force is in fact a vector quantity. The units for force are newtons, and we'll see a bit later where the units of newtons actually comes from. It has a symbol of capital N, given that it's named after Isaac Newton. Another thing to keep in mind here is that applying a force usually results in a transfer of energy. Not always. There are some situations where that's not necessarily the case, but quite often transfer of energy occurs when a force is applied. Couple of things also about a force or the outcomes of applying a force. There are a few different things that could result. So the first one is that we could have a change in the speed of the object. So notice I'm using the word speed, so we could say that it's either speeding up or slowing down. And if we're talking about changing the speed, we're really talking about an acceleration. So there's the first possibility. The second possibility is changing the direction of motion. So applying force that causes an object to, say, go around a corner. Notice that in that case that's actually also a type of acceleration because the direction of the velocity will have changed. And the last one is changing the shape of an object. So if you apply a force to something, you can deform it so that its shape becomes different. So there's some of the basics of forces. We're now going to jump across and take this a step further, and again, things that you've probably already seen, but just really trying to bed these down comfortably. And those things that we're going to look at now are Newton's laws of motion. We'll break this up into a few videos to make sure we can get into the nuts and bolts of each one of them. I'm going to abbreviate them to Newton 1, Newton 2, Newton 3. Just makes it a little bit quicker to write what it's about or which law you're dealing with. And this one is summarized as being the law of inertia. Now, inertia is the property of an object that causes it to maintain its motion. So inertia in itself is a quantity that you can look at in a lot of detail in terms of the shape, the distribution of mass, all of those sorts of things. But we're just simply going to refer to it here as the property of an object, and in this case the property that causes it to maintain its state of motion. And that basically explains what Newton's first law is about. So Newton's first law can be summarized, it's sort of stated a few different ways. The way that I'm going to state it is that an object will maintain its state of motion, and by maintain I mean that it'll keep doing the same thing. And it will maintain its state of motion while the forces on it are balanced. Now, just want to mention here that sometimes the wording that you might hear for Newton's first law is that an object will maintain its state of motion unless acted on by an unbalanced force. So it's sort of stating it in a slightly different way. I want to focus here on the fact that it's the forces acting on are balanced. It will hopefully clear up a bit of confusion. I've seen in the past a few students not quite making sense of the difference between Newton's first and second law. So if you focus on Newton's first law, it's when the forces acting on the object are balanced. Now there's a couple of scenarios here that you need to be aware of in terms of maintaining its state of motion. That basically means that stationary objects remain still, and the second thing then to keep in mind is that moving objects maintain their velocity. So they keep moving at the same speed and in the same direction. Just to try and elaborate on that a little bit more, I'll use these two examples here. So the first one will come from the stationary objects example. So imagine if you had a book on a table. So if we had our table positioned here with its legs off the bottom, so a coffee table, if there was a book that was sitting on that table, then what you would say is that the forces that are acting on that book would be balanced. So we'd look at the fact that we'd have a force acting down that would be, say, the weight of the book. So it's the weight of the book onto the table. And then we'd also have a force acting up, which would be the force due to the table pushing back up on the book. Now, in that situation, in order to say that the forces are balanced, what we're really saying is that the force of the table on the book plus the weight of the book add to give 0. So the forces are balanced, there's no unbalanced force acting on the object. What we could also then say is that the force of the table is equal to and opposite the weight of the book. So you can see there that the sizes of these two vectors are the same. This negative here indicating that the direction of the weight is opposite to the direction of the force from the table onto the book. The second example now, coming from this side, if we look, say, at a car, say on the highway, travelling at constant velocity. And the reason why I want to draw your attention to this one is that there are some of these sort of situations that trick people up because they're not careful enough about the way that forces are acting. So here's our car travelling along the road, and it has a velocity in this direction. Let's say it's travelling at 100 kilometers per hour, as you would do if you're on the highway. Now, the forces that are acting on this car, similarly to what we saw with the book, there'd be a force that's acting down due to the weight of the car, and there'd be a force acting up due to the road on the car. So we know that it's not moving vertically, so those forces vertically must be balanced. Horizontally, we'd have an applied force that's pushing the car forwards, so F with a subscript A for applied, and likewise we'd have a frictional force that's pushing in the opposite direction, that's balancing the applied force. Now, important to note here that the size of these arrows that I've drawn aren't necessarily a good representation of the size of the forces involved, but what we can say is that in the vertical direction, we've got the force of the road plus the weight of the car is equal to 0. So again, the force of the road is equal and opposite to the weight. And in the horizontal direction, we have that the applied force plus the frictional force add to give 0, or that the applied force is equal and opposite to the frictional force.